Okay, I hope everybody can see the screen. I'll start the slideshow. Let's see if we can make this. Here we are. So this is a program on floating continents. I've really had a good time putting it together for you, and I hope you'll enjoy seeing it. But so here we're just going to plunge in. These are the sources that I've used. I want you to know I didn't make this up. And we can put that on later. In the 50s and 60s, the mapping of the oceans particularly confirmed the discovery of the fact that the Earth is divided up into these many tectonic plates, which you can see in this diagram. There's also arrows in the map that indicate the direction in which these plates are moving. They're not holding still, they're moving. And you can see that in the Pacific, particularly the East Pacific, the arrows are red and really quite long, and those plates are moving quickly. The plates around the Mediterranean are green and also a little longer than average. And so you can see Africa is moving north. And over on our East Atlantic coast, you can see purple arrows, which are the average, and these plates move at about the same speed your fingernails grow. So the oceans are not getting much wider each year, but are getting a little wider. There is a mechanism for making these continents move, and that comes from the interior. The very center of the Earth, we have a core. We have an inner core and an outer core. And then we have a section called the mantle. And the mantle is about the consistency of the therapy putty that you use with your hands in PT. It's a solid, but it can flow. If you take a ball of this therapy putty and you plunk it down somewhere, it'll become plate shaped. It'll flow very slowly. It remains a solid. And so that's what the mantle is like. It's made of minerals. There are some pieces of it that have this consistency of oceanic crust, but we don't really know what most of it's made of. But because it can move, it can get some currents in it. And you can see in one place near the Atlantic, where I'm putting my arrow, that there's a rising current, because apparently there's greater heat coming out of the core in this area than it is in others. So the mantle will rise. And as it rises, it cools off, it pushes to the left and right, and it causes what we call a rift zone. In places where the mantle is cooler, the current falls, and then what we're going to see is the material on the crust of the Earth is going to get pulled back down into the center. It works very much like a lava lamp that I think most of you have seen. There are some consequences of the moving plates, of these plate tectonics. And these are the things that we're going to talk about this morning. But it's the moving plates that cause mountains to melt and plateaus to lift up. We have a rising plateau in our country. It causes volcanoes, earthquakes, hot spots, and it causes rocks to change their form. And we'll talk a little more about that. And then it's responsible for all the gems in your jewelry, the real ones. And so it does have some consequences. So these are the things we're going to talk about. A little bit about the earthquakes that occur. One of them, the last biggest one in this country, the Leume Prieta earthquake, and the one recently in Turkey and Syria. We're going to talk about Mount St. Helens, which goes way back to 1980, which we probably all remember. The Grand Canyon, Yellowstone. If you've ever been to Iceland or the Canary Islands, you've been sitting on a mid-Atlantic ridge. Oops, I left out Mohegan, it got too long. And we'll talk about the jewelry that you're going to wear. So underlying all the explanations that we give in geology for plate movement is something called a unifying theory. And, you know, this started probably about the time the crust cooled, and nobody was here when it happened. So we don't really know it exactly, but there are various diagrams that show various people's ideas of what might have happened. And this is one of them. So you can see back in the Precambrian period, there's a time scale down here at the bottom, but back at the first, where we start to record the history of the Earth, the continents are in the southern hemisphere, and the one that's going to become our continent is lying right across the middle of the equator. And the currents in the mantle, the rising and falling currents, are slowly moving these continents around the surface of the Earth. So they move kind of in what this author thinks is this sequence. And what I want you to pay attention to is a closing ocean. That's right over in here. It's called the Ibidus Ocean. And it's the father of Atlantis in Greek mythology. And there's a little piece of land here that's got a green arrow on it that's called Avalonia. And Avalonia is going to get trapped in a collision, because this is a closing ocean at this time. And as that ocean closes, Avalonia is going to get pushed closer to the surf, to this continent that later will be our home. There's going to be what's called a subduction zone in here, and we're going to get a range of mountains. And these continents all come together, and Avalonia eventually will get pushed up on this future North America. It comes in as kind of an island arc, and this ocean, the Ibidus Ocean, shuts, and this gets closer and closer. And eventually, here's Avalonia. These volcanoes get shoved on this continent, making mountains rise, and this piece of land that we've called Avalonia gets stuck. And this big continent of ours, Pangaea, forms, and our piece of land that we've been following is stuck right in here. Now, eventually, millions of years later, a rift zone develops, and this ocean that is going to become the Atlantic Ocean opens up, the continents push apart. Our continent has moved further north. We're well above the equator now. And this ocean opens up, and eventually we get back to our familiar formation. But look at these brown areas in here. These are ancient seas that covered our continents as they were getting a new configuration. And those seas are going to become very important when we talk about the formation of the Grand Canyon, because all the layers in the Grand Canyon that are sedimentary are being laid down as these seas go into the land. Avalonia is now called a terrane, and it forms, and when you look at this diagram, much of the Maine coast and a good hunk of Massachusetts. And so New England has several terranes. It's got Avalonia. It's got one that's called the Gander terrane. Apparently the oceans have opened and closed a number of times. And there's no reason to think we don't have terranes down in here. So the current theory of the Wissahickon is that it was a terrane like Avalonia. We don't have a map that shows it in the closing of the Ibidus Ocean, but its rocks are very different from everything that's right around it. And there's a fault line right where the Wissahickon formation starts. And so we think there are probably a number of terranes along the East Coast. There are a great many that have been identified on the West Coast. The Atlantic Ocean is not forming terranes right now because it's opening and has been for a long time, but the Pacific Ocean is closing. And all those pieces of land in color, we think, have come from things stuck in the middle of this closing ocean that have gotten pushed onto the West Coast. And you can see Alaska is pretty much all terranes. The best place to see this happening right now is the Mediterranean. If you go to the Mediterranean, we saw earlier that Africa is pushing north. Here's our volcanic island arc with all these pieces of mountainous land. One of them has already joined, we call it Italy, got a big mountain range up here. Probably Greece was at once a terrain. Eventually the Mediterranean will shut and all those pieces of land that are Sicily, Corsica, Crete, Sardinia, all of those will become adhered in the middle of the Africa-Europe continent that forms, and probably sometime it'll open and those will be stuck on Europe. So that's a good example of a closing ocean doing what we think the Ibidus Ocean did way back when. Will it continue in the future? Well, the answer is yes. And these are two diagrams of what one author thinks is going to happen. In 50 million years, the Mediterranean has disappeared and Africa is up here. Australia is really moving north quite rapidly. It's now straddling the equator. And at some point in the future, we'll get another Pangaea formed. We do have I can't read the names of these things. We do have one author who thinks that Pangaea is the third of the continents that have formed. And that she actually named all the ones that have formed. Let's see. She calls them Nuna, which is the top left, and then Rodinia, which is the top right, then Pangaea, that's her version, and then she's got a name for the fourth one that's going to form a long time from now. She calls it Amasya. And that she says this formation of supercontinents will continue to go on in the future. All right, so we've got to talk a little bit about these boundaries. All these different plates that are moving, carrying the land, have different kinds of boundaries. And the first kind I want to show you is called a divergent plate. And it's a place where the current is pushing up from the mantle, pushing the sides apart, and it will produce what we call a rift zone. And it's what makes an ocean grow. And that diagram shows you the sequence that we think happens. There are some rift zones currently in operation on the surface of the earth, one of them being the Red Sea. And then there's a rift zone that goes all down Eastern Africa. You can see the arrows showing what that zone is pushing apart. And at some point, Eastern Africa will break off and there'll be a narrow sea and then a larger one between them. This is an aerial view of Connecticut. There are rift zones that we have on our continent, but they're failed. They started at one time and they've stopped moving apart. There's a big one right in the middle of Connecticut. So if you drive up to New England, any parts of New England, and you go around the Hartford area, you are crossing a big rift zone that you can see in different colors there. And the way you can tell you're in it is that red rock shale. You see a lot of that around Hartford, but that's what you're driving across. That we have one in Pennsylvania, and that you drive along. If you go up to the Poconos on the northeast extension, you go through an area that has that same red Triassic shale where our continent started to come apart, but it didn't continue. They don't always develop. So right down the middle of our Atlantic Ocean, we have a big rift zone that's called the Mid-Atlantic Oceanic Ridge. And sitting on it are Iceland and the Canary Islands. And I think this is Iceland up in here. And the Canary Islands are off the coast of Africa. So if we look at their land, you can see it's volcanic. The magma that's pushing the two sides of the ocean apart is also creating volcanoes and a volcanic landscape. And so this is a picture of the landscape of Iceland. And the Canary Islands are very much the same. The top one is Gran Canaria, and you can see it looks rocky and has maybe worn down volcanic formations there. In the lower one, La Gomera Banner, you can see it's very volcanic looking. Those are probably the cores, the magma solidified cores of inside pushing up those volcanoes. We can also have boundaries that converge and produce a process called subduction. And goodness, we've got some words there that shouldn't be there. Anyway, ignore them. But in places we have the oceanic crust pushing underneath a continental crust, and or we can, and that's going to cause that ocean to contract. And at some point, the land, usually on the continental side that's being pushed up, will form a mountain range. And underneath it will be rock that's really altered, that's metamorphic rock. And that's where we're going to find gems. One of the subduction zones that you can actually see some space is a very deep Mariana Trench off the coast of Japan. And that Japan is got a volcanic island arc associated with it. And it's being pushed by the Pacific Ocean, shoving underneath the right-hand side of this page is shoving under the land on the left-hand side. And at some point, Japan will probably be joined to Asia. It's moving slowly. So earthquakes and volcanoes are very much part of this action that's going in the crust. And the Pacific has, being a closing ocean with subduction zones, has a lot of changes occurring. And it's around the edge that you can see in red. It's called the Ring of Fire. And all along the coast of the Americas, across Alaska and down the east coast of Asia and into New Zealand, we have a lot of volcanic activity. And you know, Chile's had huge volcanoes, and we'll see a couple of pictures of them, and earthquakes, and our west coast is prone to earthquakes, as is Japan. So let's see what that leads to. Anytime you have a closing ocean, you're going to get a mountain range, and that's what kind of fascinates me. The mountain ranges, the mountain belts, are shown in gold on this map. And you can see there's a mountain belt all along our west coast, all around the Mediterranean and along the east coast of the Pacific. And those are the areas that are going to have earthquakes, volcanoes, be geologically active. Our coast, which is on the east side of America, is not as active, although occasionally we get an earthquake. So the more diagrams of what's happening. We can have two oceanic plates hitting each other, and we can get volcanoes in the middle of the sea. We can have an ocean and a continent producing volcanoes, and those are diagrams that show the sequences of what's going to happen as the oceanic crust actually is pulled back down into the mantle and remelted and forms this material that we call magma. A few dramatic pictures of volcanoes that I happen to like. One of them's on Hawaii and the other is from Chile. And there can be lightning there, huge clouds of pyroclastic stuff that can be very deadly if it's breathed. And then, of course, if you get a certain kind of lava, it will flow, like what's in Hawaii. Okay, so let's talk about Mount St. Helens. Mount St. Helens is in the Cascade Range, and our Pacific Ocean is the crust is being pulled back down into the mantle. It's being remelted, and it rises, it collects in pools that are in the crust, and eventually it can rise to the top under and push up a mountain and even explode and cause a volcano. There are lots of warnings when this happens. Earthquakes, we don't have a lot of warning for, but for Mount St. Helens, there were a lot of warnings that started in March of 1980, and that volcano didn't blow up until about 2 months later. So as the magma pushed up, which you can see in that sequence of diagrams, it's going to cause some earthquakes. There were a lot of warnings given to people to stay away from that mountain. They were pretty sure it was going to blow up, but nobody knew when. And there were some people that died in that explosion because they went into this beautiful area around Mount St. Helens. But on May 18th, which is the third diagram down, you can see the side of the mountain is blowing up. That magma has dissolved gases in it, and water that's expanding. And so it's like the top coming out of a bottle of Coke that you shake, or seltzer. It just blows things up. Yeah. Okay, let me get it out of the way. Yeah. Okay. All right. That's helpful. Okay, we can go back. Anyway, you can see the eruption was huge. This was what it looked like from Portland. This huge cloud. It looks almost like a nuclear explosion, doesn't it? Let me see if I can go back. No, it doesn't want to do that. It doesn't want to go forward either. Oh, well. All right. I got to outsmart it. There we are. When the mountain explodes, a lot of the earth is removed from above it, and it may result in a crater that can form either a lake, or it might be molten and fill up with magma and would be what we call a lava dome. And that series of diagrams shows the explosion removing all that land and then forming this deep depression from what the exploded material disappeared from. And then in this diagram, there's a lake at the bottom, but the magma is pretty close to the bottom of the lake. And see if this, for Mount St. Helens, we get a crater, but instead of a lake, there's a big lava dome. Over a third, maybe 2/3 of that mountain was blown away in the explosion. And I did miss a slide, but I'm going to go back. That's what the series looked like. This was the mountain ahead of time. And this was the initial explosion. And that was a series of photographs that was taken by a photographer who did survive, but was close enough to get those pictures. And that showed, here's the crater. Yeah, and that this lava dome it has magma in it, and when it starts to grow and get bigger, then that's going to be a sign that this volcano may be becoming active again. But right now you can visit Mount St. Helens and see the recovery that's occurred. A lot of destruction around that with forests and mud flows, but the area has come back beautifully. There is a whole arc of mountains that are similar to Mount St. Helens along the west coast. We call it the Cascade Range. And there's a fault line right in here called the Cascade Fault Line right in here. What is this doing? Okay. Oh dear. We're going to have to take a pause for a minute and find our way back. Here we are. Yeah. Let's see if we can.
Sometimes if you close and then reopen.
Yeah, I'll close the share.
Yeah.
And then reopen it. Yeah.
Try again.
Okay, let's try sharing again and see if we can get this. Okay, here we are. And we'll get this out of the way. Thank you for your patience. Oh, just want to move it. Okay, now we've got to find our way back into the program. Okay, here we are. Okay, so let's hope this doesn't happen again. We have our mountain range, we have a fault line. This is where there's a subdivision of the Pacific Plate called the Juan de Fuca Plate. And this is where the subduction zone is occurring. We get marvelous sunsets after huge volcanoes. I don't know if you remember the sunsets we got after Mount Pinatubo exploded in the Philippines, but sometimes for a whole summer, you get these beautiful, beautiful sunsets. And we got good ones there. Yeah. That picture was in New York. It was a pier. Yep. All the debris there. Okay, a third kind of plate movement. We've had the kind that spreads apart. We've had the kind that subducts and moves together. And then there's one called a transform fault, where the plates actually slide past each other. And our San Andreas fault is a sliding fault. The part on the left is going up in the picture. The part in the right is going down. And you can see where over time you get an offset where there was a stream that now has that goes around a corner, or the stream bed does. What happens in these faults is that the fault is moving very slowly. It's working a little bit like an elastic. That tension builds up between the two halves of the fault. And for a long time, it's just building up tension. But then the tension gets great enough that it snaps. And that's what happens in these transform fault earthquakes. We had one in 1989 in Loma Prieta. Remember, people were caught in a baseball studio and at a baseball game, and they had trouble getting home. But there was a lot of destruction. The picture on the left shows the waves that occur with an earthquake, and they're used for studying them. There was a lot of damage to one of the major highways. So this was not a really great earthquake. Our country and Japan and other well-developed nations have built so that the buildup tension in their earthquakes can be withstood by a lot of their buildings, but not so in the recent one at Turkey. There is a fault called the Anatolia Fault, and you can see the different fault lines, but the place where the earthquakes occur are shown in the red and orange dots that ran through northern Syria and eastern Turkey. And a part of the devastation that occurred there was the tension had built up, the sides snapped, and then there were a lot of aftershocks. There were a great many earthquakes that are shown in those dots. The buildings were not built to the kind of code we have and collapsed with a great loss of life. And also the population density is very great in that area. And so that's one of the big tragedies that has occurred. But due to plate tectonics, remember, Africa is pushing north, it's cracking the land. That's where these faults develop. Okay, so we're going to go to something that's happening in two places in our country, in our 50th state, Hawaii, and also in the western part of the United States. But in addition to having these rising currents and falling currents, we can also get from the mantle things called hot spots, where the mantle is rising, not in connection to a convection cell, but there's just a probably fairly narrow plume pushing up, and it's causing volcanoes to occur that are not part of a mountain range. And we have very famous one in the Hawaiian and Empress Seamounts, because the Earth's crust, remember, is pushing, in this case, it's pushing northwest, and it's over hotspot. So this whole trail of mountains that you can see across the ocean are places where the crust was exposed to the hotspot. Then the crust is pushed a little further along, and the hotspot affects a different part of the crust, and we get a different chain of islands there, with Hawaii being the most recent one, with volcanic action occurring under it. And there are some suggestions that new ones are starting to form. Eventually, Hawaii will move with the crust off that hotspot and will no longer be quite as active, and will start to get run down by the sea, just eroded by the sea. The big one in our country on the continent is called Yellowstone, and it is being pushed. We are being pushed towards the west, and so we have a whole line of places that are marked in this line here of where that hot spot used to be. And a number of years ago, you can see the time scale. And the Yellowstone caldera, the Yellowstone volcanic area is now up in here. And you can see there's all kinds of geological activity around it. And so this is an aerial view of Yellowstone National Park with its lake and surrounding mountains, and a map. Now, Yellowstone has a huge caldera in it, and it actually covers an area larger than Delaware and larger than Rhode Island. It has earthquakes occasionally, and you can see where they've been marked, a couple of them. It probably has, these are major earthquakes, magnitude 6 and 7. Its caldera is right around here, and it's got a lake here, but all of that area is part of Yellowstone Park. Now, it has 3 canyons in it that form along the edge of the caldera. And although this diagram says it's semi-dormant, it's, let's say, at a low level of activity, but it's not really dormant. And there are places where we're going to see the activity. But what's happening is this hotspot plume is pushing up underneath, and it's pushing up under this big caldera. We get earthquakes on both sides, and this big depression in which the central part of Yellowstone lies, you can see in this diagram. Geysers, hot spots. This is the view of the Grand Prismatic Spring, but that water is so hot, it would scald and kill any living thing that fell into it. I found one picture with the steam coming up, and that's they're called the paint pots, huge amounts of energy. There are boiling mud cauldrons all through Yellowstone. There are geysers in a great number of locations. There's a North Geyser Basin is the lower left, and the Steamboat geysers are on the right. We also know Old Faithful is one of the geysers. It's not erupting quite as often now as it did when we were kids. But here's what happens. That magma pool that we saw in an earlier diagram is pushing up. And this is the formation of what was called the Lava Creek explosion 600,000 miles ago. The hotspot sent up a column of hot magma, forming a huge chamber. There is a chamber current chamber under Yellowstone now, maybe not quite that big. It pushed up a dome. It caused cracks in the surface. Surface pressure increased to form cracks, and we get a massive explosion with a huge amount of lava. And the extent of that Lava Creek explosion is shown in the lighter colored area, but it covered over half of our country. Now, this is 600 thousand years ago. It's very long ago. And so I don't know whether there were people here or not. The roof of the dome is going to collapse, and lava continued to flow into this caldera for 50,000 years, and it filled much of the craters. There were mountains around it, and they collapsed into the crater. And we find volcanic rock. There was a huge lava area where mountains were collapsing into the ground due to this massive explosion. Yellowstone is still an active volcanic area and provides the heat source for all those thermal features that we looked at. There are, these are the lava columns that we find in Yellowstone, where lava has pushed up. Lava columns have this kind of tower formation all over the world. If you've been to the giant steps in Ireland, that's what you're looking at. It's a very common rock formation, and it is evidence that there was a lot of lava flowing into that area. So we're going to go visit the Grand Canyon, which also is being produced. It's being produced by the Pacific Plate shoving under the North American Plate and causing the Colorado Plateau to rise. And this is its story. The Grand Canyon is produced by the uplift of the Colorado Plateau as the Pacific Plate sinks under the North American Plate. And the river, which has been in place for a long time, is just cutting through this uplifting plateau, because that rock that's shown in the green color is fairly soft. It's sedimentary rock, and it resulted from the inland seas that we saw in an earlier diagram that existed at another time. This is a satellite picture of that Colorado Plateau on the left, and then there's a more current aerial photograph on the right. And in the Mesozoic era, ancient seas covered this area, laying down over time many kinds of volcanic rock. And this is the added information. It doesn't fit on the diagram. But many of the layers were deposited in a warm, shallow sea, near shore environments. There were like beaches and swamps where sediments could collect. And the shoreline repeatedly advanced and retreated over the edge of Western North America. There was one major exception that they've identified as not being an ancient sea, and that's believed to have been formed from dunes, from sand dunes that were blown. So at some point, this land may have lifted above sea level. And then there's one section that's called the Supai Group that must have been, they think it was fresh water that invaded that area. So it has a very long history. Now, these are the layers over time. Let's go back. And down here at the bottom, see if I can get my arrow here, there's something called an unconformity. There was a time when the land just eroded away and the deposited layers were lost. They just disappeared. They washed out to oceans. And these are even more ancient deposits down below that. But then you see some slanted, lifted up, deposited areas underneath. And so those were from what would have been a volcanic area where there was actual mountain building. And there is just above the unconformity, this is a layer of lava in here and something called an unconformity. Do you need, could somebody go get her assistant? Not Cat. No. Thank you. All right. Yeah. Okay, and these are just some beautiful scenes. I'm sure a lot of us have been to the Grand Canyon and seen those. It's up to over a mile deep in the bottom. And that oldest layers at the bottom are believed to be about 2 billion years old. And the top one it's called the Kaibab limestone is probably a 230 million years old. So it's a huge amount of geological history that's in there. Very deep in the canyon, we found older layers of rock that are volcanic. And this is way down in the canyon. And volcanic lava down at the bottom, which are the roots of a very ancient mountain range that eroded away before the Grand Canyon sedimentary sea layers were laid down. Okay, so now we get into the point where we need to talk a little bit about where your jewels came from. This is a picture you've seen before, but it shows a subducting boundary, a converging boundary. And this is a place where rocks are buried, subjected to a lot of heat and pushed down to the bottom. And this is where gems are formed. It's in metamorphic rock. You can get some gems in igneous rock as well. Okay, so we'll keep talking a little bit about what's happening in the Wissahickon. The Wissahickon we mentioned is probably one of the terrains, and it was in a metamorphic zone, and it has a lot of gems in it. The one on the upper right, it looks like a chocolate chip cookie. It's got garnets in it. Now, garnets are a crystalline substance. They have some kind of metallic ion in them, like iron or sodium or potassium, and they have a lot of aluminum, and they're silicates, and they form crystals, and they're present dispersed as molecules in the molten material that was undergoing metamorphosis. So as this material flows, like the therapy puppy that we talked about earlier, those molecules can find each other, and when they do, they join and they form a particular kind of 8-sided crystal for garnets. And so that's what happened in that one that looks like a cookie. It's not gem quality because it has a lot of stuff in it called inclusions, but it's the way the garnets that you have in jewelry form. Mica forms the same way. It's a silicate compound that forms crystals, but its crystals have a different shape. They form a big sheet. And so any rock that you find with mica in it is one of these rocks that was caught in a subduction zone, has undergone metamorphosis, and is forming gems. It doesn't take a whole lot of temperature and pressure to form mica. So the gems that we have in the Wissahickon are called index minerals, and they can tell you a little bit about the temperature and the pressure that these gems were subjected to. So we get schist and the two kinds of schist, silvery and black. We get them somewhere between 150 degrees and 600 degrees. We get garnets. When we have garnets, we know that it was a higher degree of metamorphosis, more heat, more pressure, somewhere between 450 and 700 degrees. When we get the mineral called staurolite, it was between 500 and 600 degrees. So these are index minerals. They tell us a story. And if we get the kind of rock that's called gneiss, it's even a higher level of metamorphosis. And then the stuff, and these are all Wissahickon minerals, the mineral that almost got melted back down into magma during metamorphosis is called migmatite. And you can see all these kinds of rock in this park that we're right next to. All right, but let's talk about the gems because that's kind of fun. And I thought I would talk about emeralds, rubies, diamonds, garnets, and opals. And they're valuable because when they formed crystals, there are not as many inclusions, there's not as much other stuff that's incorporated in that crystal. They're clear and transparent. And you can get garnets in certain places that are clear and transparent, and they have a color that's based on some kind of other pigment that's in, or other kind of mineral that's associated with them. So we'll do emeralds first. They're made of beryllium, a very rare compound containing beryl, aluminum, silicon, and oxygen, caught in a metamorphic zone, probably a subduction zone, with very high temperatures and at a very great depth, probably miles underground. And the crystals are attracted to each other and they'll join. And if the crystal is clear and it has traces of chromium in it, it'll have a green color. And it sometimes can have stuff in it that makes it bluish green. So you can get different shades of emeralds, but it's going to be clear. Now we get the stuff coming to the surface because the land over it gets eroded. And so it can be mined, it can be found below the surface. Rubies and sapphires are both molecules. They're forming crystals of a compound called corundum, and that's an aluminum oxide. And during metamorphosis, these molecules can move together. They form crystals. If the crystals are clear and transparent, they would be gems. Sapphires are blue because they contain traces of iron and titanium as impurities, and rubies are red because they have chromium. And we wouldn't have them if we didn't have colliding continents.
I have a question, Sarah. Are there certain areas of the world where these are more prevalent?
Yes, there are. Yeah.
I keep thinking about Earth.
Yeah. Yeah. And I thought diamonds and diamonds, form Africa in Ethiopia. There are diamond mines, there are other diamond mines, but these have a different formation. They form from carbon trapped in the mantle in the form of graphite. Graphite is found in pencils. And they're way deep, 62 to 120 miles below the surface. They require immense heat and pressure, and it changes a graphite sheet of carbon molecules into a more triangular form. And then they get brought up to the surface in these vertical pipes, kimberlite pipes, when magma eruptions occur. And so these kimberlite pipes can reach the crust during plate movements. And again, these diamonds are going to be clear if they're going to be gems. If you get a blue diamond, it has traces of boron in it. And so they're a little different. Now, opals, and I happen to think opals are really lovely. They're not crystalline at all, but they have to form when rocks have been deformed and there are cracks in them. And they form from silicon, oxygen, and water compound called silica. They're very heavily hydrated, have a high concentration of water attached to the molecules. And then this water seeps down into the cracks that are formed when plate tectonics occur. And gradually the water evaporates and the silica precipitates and it leaves an opal behind. Some of these opals don't have a whole lot of color in them, but others have beautiful colors in them. And as the silica slowly infiltrates the fractures and cavities in rocks, Australia has wonderful opals. And you can get sometimes fossils that are opalized that have this material around them. But this wouldn't happen if we didn't have floating continents. All right. So I think your brains must be full. Enough is enough. So I'm going to end the talk here and let you ask some questions. And I do think we have some chemists here. And so maybe you'd like to even make some comments. Sometimes an accumulation of knowledge is a good thing. But I think the world is really a pretty beautiful place, created by these floating continents. It can also be terrifying for the same reason. But I love this little North American proverb. We do not inherit the land from our ancestors. We borrow it from our children. And so I'll put a plug in for taking care of it. All right, I'm going to stop sharing my screen right now. And we'll go back to our form here. And if so, let's take questions first from classroom 2. And could I find some people that would distribute the mic? Yeah. Thanks. And Charlie has a question. Charlie Day. Keep going, Mary. Okay.
Okay. Going?
Yes.
The whole earth was billions of years ago, I don't know when. So everything was formed at the same time. So I'm always puzzled by when somebody says this layer is 2 million years old and that layer is 8 million years old. How come every layer would be older than another one and they're all starting at the same time?
The Earth didn't form exactly like it is today.
Could you repeat the question?
And the question is,
Sarah.
when the Earth was formed, it was formed about 4.5 billion years ago. And the question is, how did the layers become different if the Earth was formed with everything in it that is currently present? And the way the elements and the molecules were arranged 4.5 billion years ago is not the way they stayed arranged. There were changes in Earth chemistry that occurred over time. That's Eva Marie back there, isn't it? Okay, is that a satisfactory answer to you? No. Okay. Yeah, over geological time, huge changes have occurred. Now, probably all the elements that we have today were present, but they were not in the form that we find them today. The surface was probably molten, and it took a long time to cool off. And while it was cooling off, this molten material, which we've described as being like therapy putty, could move, and the molecules in it could move around, find each other, form crystals, cool off, rise, sink. So there are a lot of changes that can occur while the Earth is in that heated phase. Then it cools off, water can form in liquid, can accumulate in liquid form in clouds. We start to get the action of water. It's going to have a huge effect on the surface of the Earth. And is that a satisfactory answer to you?
I'm sorry, please. Figure that out, so let's go on to the next one.
Okay. Do we have another question? I think Charlie had one. You didn't? Okay. Yes, comments are very welcome. And
you know, I visited Medicine House in 2000, and you go into the visitor center, the big auditorium, and you watch a film about, you know, all the history that Sarah just gave us. Then they pull the screen apart, and where the movie was being shown is actually a window that shows you the mountain. And it was just so impressive to suddenly see this blown out mountain. And the whole time driving up into it, I mean, it's just the landscape. This was 20 years after it happened. Landscape, just this gray rock. It was very, it's hard to find words to describe it because it was so impressive about total change from what we're used to of a living earth with plants on it. There were a couple little plants places. It was very impressive.
yeah, and if I can just keep working on Eva Marie's question, when life forms and plants develop, they also have a huge effect on the surface of the Earth. Tama? Do you want to come on up here and then talk so the folks on Zoom can hear you?
Sarah, I think it's clearer if they speak into the computer rather than the mic.
You won't be able to hear. Okay, go ahead.
There's a lot of interest in climate change right now. And given the inexorable things that have gone on over the past billions of years, are we just fighting a losing battle? Is the Earth going to do this climate thing whether we try to stop it or not?
I think that's above my pay grade. But the predictions are that even if we were able to stop putting greenhouse gases in today, which we can't, that the temperature would continue to rise. Now, I do think the Earth is going to be affected by climate change. There will be more floods. There'll be more erosion. That there'll be more fires. I don't think that climate change will affect volcanoes or earthquakes, but certainly the surface of the Earth is going to be subjected to greater erosion. And I think that human beings as animals living on the surface of the Earth that our numbers may very well go down. At some point, the death rate may exceed the birth rate. So I would suspect that plants and animals on the surface of the Earth would be affected by climate change. Okay, we have another question or comment?
Yeah, I have a question, Sarah.
Go ahead, Anne.
Would you repeat what you said about the formation of the Appalachian chain?
That occurred when Pangea formed. At that point, the ancestor of the Atlantic Ocean was a closing ocean, much like the Mediterranean is today. And there was a subduction zone off our east coast where the crust, the oceanic crust, pushed underneath the continental crust and caused a big wrinkle. And we called that the Appalachian Mountains.
Thank you.
And it actually appears on both sides of the Atlantic now. The Caledonians mountains in the British Isles are continuous with our
Oh,
Appalachian range. Yeah.
so how does that contrast with the Rockies?
It's the
they're
same
much younger.
formation. The
Oh.
reason the Appalachians are not as high is that they are much older and they've been worn down by erosion. And but probably they were as high as the Himalayas when they formed. And it is noontime now. But if anybody has some questions and they want to stay, we can leave the meeting open. Is that okay, Diane? And please
can.
feel free to go have lunch or whatever you need to do at 12.
There's a question in the family room.
Okay.
Yeah, go ahead.
This is Dallas. Some years ago, we felt tremors in Pennsylvania and Maryland and Virginia. Are we sitting on a fault?
Yes, thank you, Dallas. That's a good question. We do have some faults that run through this area, and they're probably transform faults where stuff moves by, things move past each other. But our earthquakes are nowhere near as big as they are in the places where there's active subduction. So we do have some slow amount of movement here. We had an earthquake that put a crack in the George Washington Monument a few years ago. And I've experienced little tremors here. When we had one and I was living in a house, all the windows rattled in their cases. And the next morning it was determined there had been a very mild earthquake. And there are some earthquakes along the Mississippi Valley.
Thank
There's
you.
a fault zone in there called the New Madrid Fault Zone. And there was a pretty big earthquake there at one time.
Thank you very much. But it was
Yeah.
Sarah, rather than leave it vague as to when we're closing, I am going to close the meeting for Zoom. And I think you can find Sarah and ask any questions that you have left over. This was an amazing presentation. Thank you so much.